So I want to look at some examples of using polynomials. Some of these come from our notes where it was actually error. And so we're just going to omit the error sections since for this particular year's AP exam, error's not on there. But I still want to look at some of the other questions because I think they're still pretty good questions. And so I'm going to kind of jump around. So follow along. Certainly feel free to pause the video, try the examples first, then go back and watch it and see if you did it right. So, a third degree Taylor polynomial for the function e to the 3x centered at c equals 1. Okay, this is one step farther than just like manipulating e to the x to make it e to the 3x, because now we're also centered at 1. So there's going to be one extra step we have to be really certain to do. But I can start off with just knowing that my function e to the x is n equals 0 to infinity of x to the n over n factorial. So we know that. So it's really easy to manipulate it to make it e to the 3x. Simply where there's an x, replace it with a 3x. So n equals 0 to infinity, and then, 3x to the n over n factorial. So there's a Taylor series centered though at 0, not centered at 1. In order for this to be centered at 1, I have to make sure that our radius is centered at 1, or x minus 1 would be the center of this function. So I need to change this side to an x minus 1, which means I can change this side to an x minus 1. So that gets us a little bit closer. I'm sort of laughing because even though I'm using a pen, it's for some reason, the eraser icon is showing up. So that's fun. Let's see if this changes it. Nope, does not. 3x minus 1 to the n over n factorial. So we're closer. But now we don't have e to the 3x. We have a different function. So I can certainly rewrite this as e to the 3x times e to the negative 3. And so I can isolate that e to the 3x. And then that is equal to the summation n equals 0 to infinity of quantity 3 x minus 1 to the n over n factorial. And then simply by putting this to the other side, you're dividing it across. Since it's a negative exponent, it's just like multiplying. So then we could say e to the 3x as a function is equal to, actually, this will be a whole Taylor series, not a polynomial yet, because remember, a polynomial is finite. We'll have an extra e cubed, and then 3x minus 1 to the n over n factorial. So then we want to go ahead and we know it's centered at 1 because this is x minus 1, and then we know it is our function e to the 3x. So we want to write the third degree Taylor polynomial, so we just choose n equals 0, 1, 2, and 3 to figure out what that value is. So our third degree Taylor polynomial, when n is 0, this is just e cubed, plus when n is 1, so then when n is 1, we get e cubed times, let's see, what does that be? 3 x minus 1 to the 1 over 1 factorial, plus when n is 2, we get e cubed times 3 squared, which is 9, x minus 1 squared over 2 factorial, and then when n is 3, we get e cubed times 27 x minus 1 cubed over 3 factorial. And again, AP exam does not care that you don't simplify. You could leave things just like that and you'd be fine. So I thought that was a good problem. Okay. So then another example I want to do is still kind of focus on the e to the negative x. So it did say find the error using a third degree Maclaurin polynomial to approximate e to the negative 0.4. Well, we're not going to find the error, but maybe it would ask us to approximate that value using a third degree Maclaurin polynomial. So we know it's centered at 0, and when it's centered at 0, it makes manipulating e to the x into the e to the negative x really easy. And you remember, like e to the x we said was equal to the summation n equals 0 to infinity of x to the n over n factorial. Since it's going to be centered at 0, e to the negative x is equal to summation n equals 0 to infinity of negative x to the n over n factorial. And so if we want a third degree Maclaurin polynomial, so then we could say, okay, m sub 3, I guess, is equal to, so when n equals 0, we get a 1. And then when n is equal to 1, we get negative x over 1. When n is 2, we get x squared over 2 factorial. And then when n equals 3, we get minus x cubed over 3 factorial. So really, it makes it an alternating series. And if we were to use error, we'd be able to use the alternating series error test, which we, the first man out would bound your error. But we don't have to. And then if we were going to use this to approximate e to the negative 0.04, that means that our value is negative 0.04, right? That's what we're put. Well, actually, I take that back. It's actually 0.04 because we already have it as e to the negative x. So we would just say, okay, that is equal to 1 minus 0.4 plus 0.4 squared over 2 minus 0.4 cubed over 3 factorial. And I know I'm inputting 0.4 because if you take a look, the only difference between this and this is that the negative is already there, right? You're choosing x to be 0.4, but it's already negative as a function. So just be careful of that. Okay. So I like that example. And then let's see, what else do I have on this sheet? Again, a lot of these are focusing on e to the x. I think that's going to probably be a common question that could show up. At least it usually does. Now that they're only limiting it to 2, maybe it won't be. But I know in the homework there's practice with sine and cosine or creating your own function. So same idea, how would you approximate the value of e? It's just e to the x, and e is the same thing as e to the 1. So if I think about, it does say Taylor polynomial, but if it's centered at 0, we know it's a Maclaurin. So we know e to the x is equal to the summation n equals 0 to infinity of x to the n over n factorial. So then when we're we're just listing out for the 5th degree, it'd be 1 plus x over 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th power over 4 factorial plus x to the 5th power over 5 factorial. And in this case, we're letting x be 1, so then that would be 1 plus 1 plus 1 over 2 plus 1 over 3 factorial, which is 6, plus 1 over 4 factorial, which is 24, plus 1 over 5 factorial, which is 120. So there is an approximation of e. And then that's actually, it's kind of like a cool way to define e, another way to define e. And obviously the higher degree of your polynomial, the more accurate you're going to get for that particular approximation. Now for this one, it doesn't alternate. So if we were to use an error approximation, we'd have to use Lagrange, which is fine, but we won't be tested on that for this year. Okay, I think I have a couple more. So I'm just going to go ahead. Oh yeah, so this one's kind of cool. It says, use a power series to evaluate this particular, this particular series, or this integral. And the thing is, we don't know how to integrate this. We know how to do natural log, but integration by parts, or just memorize it, but not natural log of 1 plus x cubed. But what I do know is that I have a power series for natural log, and it's been a while, maybe since you've seen this one. So we do know a natural log of x. It's an alternating series, n equals 0 to infinity of negative 1 to the n times x minus 1 to the n plus 1 over n plus 1. And remember, this is centered at x equals 1. That's the 0, quote unquote, of this particular function. So then, if that's what natural log of x is, then natural log of 1 plus x cubed could be manipulated by n equals 0 to infinity of still negative 1 to the n. And then when I'm putting the quantity 1 plus x cubed in here for this x, and I subtract 1, it's just going to be x cubed to the n plus 1, which is kind of cool, all over n plus 1. So now I'm going to integrate that. So then when we integrate this from 0 to 2, so then remember we're integrating this as a power, so like the powers are going to go up, they're going to increase. So then we get the summation n equals 0 to infinity of negative 1 to the n times x cubed. Now really this was like x, well yeah, I mean like that's fine, like you think of it like as x cubed to the n plus 1, which is also, you could think of that, if this helps, is x to the 3n plus 3. So one more power would be x to the 3n plus 4. Or if you think about that's probably the easiest way. So that's x to the 3n plus 3. So one more power, x to the 3n plus 4, and then all divided by n plus 1, which is originally down there, and then 3n plus 4 here. And we're going to evaluate that from 0 to 2. So the fact that we're putting 0 in here for x, so 0 to that power makes it 0, which is nice. So then when we actually put in 2, we'll just get whatever. The summation n equals 0 to infinity of negative 1 squared times x to the 6 plus 4 is 10 over 3 times, again, 6 plus 4 is 10, or the summation n equals 0 to infinity, negative 1 squared is just negative 1, x to the 10th over 30. And again, depending on what x you choose, I'm so silly. I substituted not for, did you see what, catch my mistake? I substituted not for the n's, but I forgot to put it in the x, not the n. So let me fix that. I was like, wait, that doesn't look right. Let's try that one more time. I like my integral though. Let's try that one more time. My bad, because the bounds are x's, not n's. So again, I don't know where these yellow marks are coming from. So we have this summation, n equals 0 to infinity of negative 1 to the n times 2 to the 3n plus 4 divided by n plus 1 times 3n plus 4. There it is. And then if we would have put in 0, realize that this x here being a 0 would have made that whole thing equal to 0. So here's my answer. It looks much better. Sorry, it's an early morning. You could call it a Monday morning, but it's not because it's Wednesday. So yeah, and then you don't have to evaluate anything. You don't have to solve for anything. You don't have to prove if it converges or diverges. That's it, which is pretty cool. I think this video has one more example. Yeah, another question, kind of like an AP practice question. And again, we may not do all of the components of this only because, we're not going to do error for this particular, for this particular year for the AP exam. Okay. So let's write the first 4 terms in a general term of a Taylor series expansion for f of x about x equals 2. So that means we're centering this at x is equal to 2. So, this sort of looks like a geometric series, but if I want to make that into a geometric series centered at x equals 2, I need to make sure it's like x minus 2, like that. So I've just introduced a minus 2, so I better add a plus 2 there. So negative 1 plus 2 is actually 1. That actually works out to my advantage, 1. And then that's plus x minus 2, because when I start to try to write this as a geometric series, the non-negotiable is this has to be a 1. It's a over 1 minus r. And so then to get that minus r, don't forget we just do a double negative, minus negative x minus 2. So there's my function that's centered about x equals 2. So if I'm going to write the Taylor series for that, remember if you have, go to a different color just to change things up. So if you have a over 1 minus r, remember that is equal to the infinite series, summation n equals 0 to infinity of a x to the n. That's our geometric series. So that's what we have. Our a is 1. So then we get the series n equals 0 to infinity of negative x minus 2 is a quantity to the n. Remember, because our a was 1. Now, if you don't like that negative inside there, you could certainly rewrite it as an alternating series. So you could say negative 1 to the n times x minus 2 to the n. So there's the general formula for that. That would be a general term. And I guess if it's just looking for the term, it'd just be the part that's within the summation, for that particular one. And then if we were to write out the first 4 terms, so notice it says first 4 terms, not 4th degree. So first 4 terms is actually going to be the 3rd degree. So when n is 0, we get 1, and it's going to be positive. When n is 1, it's going to be minus x minus 2. When n is 2, we get plus x minus 2 squared. And then when n is 3, we get minus x minus 2 cubed. So there would be the first 4 terms and the general term. Okay. It says use the results for part A to find the first 4 terms and general term of the series expansion about x equals 2 for the function the natural log of x minus 1. Okay, so we already know what the natural log of x is, so we could have easily manipulated that like we did in the previous example. In terms of that particular function. Now, if they want us to think about it from using our results in part A, we can realize that if I were to integrate, just think about the antiderivative, go this color, the antiderivative of 1 over x is equal to natural log of x plus c. Right? So the antiderivative of 1 over x minus 1 is equal to the natural log of x minus 1 plus c. So if they want us to use the results from part A, and we know that we have an expansion of natural log of x minus 1 centered at 2, which is this, right? Which is this right here. So if that's what we have from our results, that's what our function is, f of x. If we integrate what we have, then we will get our desired function. So I'm going to use, even though I could have done this another way, I'm going to use that result. I'm going to integrate our result. So part B, I'm going to integrate 1 minus x minus 2. And the thing about the AP exam, when they are free response, at least in the past, everything's been related. So this makes it a very feasible question, like, oh, are you're just basically seeing I can integrate all of these terms to obtain that function. So then that could be x minus x minus 2 over 2 squared plus x minus 2 to the 3rd over 3 minus x minus 2 to the 4th over 4 plus a constant of integration. So there we go. Now, part C, it does say use part B, compute the computed number that differs from the natural log of 1.5 by less than 0.05, justify your answer. And this is where we wouldn't have to do because we're not calculating error. But since, again, relating to what we know, it is an alternating series, so we could use AST, and figure that out. But I just liked reiterating, or showing how you can integrate a series to help you evaluate that. And that's what I really liked about this example up here too. Where we weren't able to actually evaluate this integral, but we were able to integrate it via knowing how to write it as a Taylor polynomial. So, okay. So I know this is a little bit longer video, but I thought that they were good examples to go through. So